Hey, all you cool cats and kittens. Today we're going to be covering analysis of variance, also known as ANOVA. Um, Gets a little complicated, but I'll make it easier for you in terms of what I'll be testing on. But with that being said, let's get it crack-a-lackin'. So with analysis of variance, here we go. So it's actually a one-way analysis of variance that we're going to be discussing today. And just for this class, we're not going to get into two-way or anything more complicated than that. We're just going to stick with the one-way analysis of variance. So these last couple weeks, we've talked about different t-tests. We've talked about independent samples and dependent samples t-tests. Just keeping in mind what those are. We're comparing for independent samples t-test, one independent group to another independent group. Those independent groups mean that they are between subjects, meaning that the people in one group are not also in the other group. So if we were to compare our stats class to Professor Greenwood's stats class of the same semester, that would be a between subjects design because no one's in two of the same class twice in the same semester, or the same class twice in one semester, whatever. But I have a different group of students in our class than Christopher Greenwood has a different group of students in his class. So that would be an independent samples t-test if we were going to compare those groups for any reason, for test scores or sanity levels or attractiveness or whatever, I don't know, anything. That would be an independent samples t-test. Now, a dependent samples t-test is we're comparing one independent group to another, or dependent group to another, excuse me. So that would be if I was going to give you the final of this class on the first day, and then we take the class, and then I give you that same final on the last day of class. It's still the same 29 of you, the same 30, the same 50, the same whatever number, the same group of people is taking that test twice. So you guys are in the same conditions twice, but you're just being tested at different times. That would be a dependent samples t-test. We're comparing one dependent group to the other. I expect there to be a change in your scores from the first time you take the test without knowing anything about stats and the second time you take the test after taking the class in stats. So ANOVA is a little differently. So whereas with independent and dependent samples, we're comparing two groups, be it independent groups like our class and Greenwood's class, or dependent groups like before you took the class and your test grade on the exam and after you took the class and your test grade on that same exam. However, ANOVA is comparing more than two groups. So an analysis of variance is comparing three or more groups on something. So just to kind of think of how to think about that, just to kind of get into an example of that. Let's say we can make an analysis of variance by comparing our stats class to Christopher Greenwood's stats class to Dr. K. Burtkin's stats class. We can compare three different stats classes. Essentially, in that example, analysis of variance is just adding another condition or factor, as I'll talk about it later on, but it's just adding another group. So instead of comparing, two groups, now we're comparing at least three. So to get an example to get kind of a visual, let's say that a professor is going to provide feedback and see how different types of feedback alter a student's self-esteem score. So maybe it's an essay, let's say. I know we don't have essays in stats, thank God, but at least I don't assign essays in stats. But anywho, so, excuse me. So let's say that we have three groups, right? And an analysis of variance means we need to have three groups. So for one group, they're provided no feedback on their essay. So they get it back, they get a grade, and it's like, there you go, deal. The second group is provided with positive feedback. So, oh, you had really good sentence structure here, or, oh, you made a really good point here, or, oh, I like where you're going with this, or whatever. The feedback that they're receiving is positive, even if they're having issues, even if they're struggling, like, oh, you can do a little better on your sentence structure here, but overall, really good work, just provided positive feedback for the second group. And the last group out of three, is being provided negative feedback. So this is garbage, what were you thinking? Or this is incorrect, make it better. More just negative feedback. So we have a group that has no feedback, just a grade, and here you go. We have a group that has positive feedback, like, oh, you're doing great, you know, try doing this, more constructive. And we have the negative feedback, which is just, Rah! So, you know, we're comparing those three groups in terms of self-esteem. So for ANOVAs, this, you might notice at the top here, 3 groups, K equals 3. That K is just represents the number of groups. So when we talk about K in ANOVA, it's just talking about how many groups do you have? Well, we have 3 groups, no feedback, positive feedback, and negative feedback. So our K, the number of groups we have, is equal to 3. So with ANOVA, we're testing if the groups are different. So is the no feedback group different than the negative feedback group? Is the no feedback group different than the positive group? Is the positive different than the negative? We are testing just to see if they're different. With ANOVA, since we have 3 groups, just ANOVA itself does not tell us which group has higher or lower rates of self-esteem or test scores or whatever it is that you're comparing them on. That's an extra step in ANOVA. But in terms of when we reject the null hypothesis for ANOVA, when we say, hey, we have statistical significance, all that's telling us is that, hey, the self-esteem scores for these 3 groups are different. We don't know which one's higher or lower. That requires an additional step. But when we reject the null hypothesis for an ANOVA, that's just saying they're different. It's a little easier to tell when we had dependent or independent samples t-tests, because we're just comparing one group to the other. We don't have to worry about, well, which group is, you know, which groups are different. We only have the 2 groups. Obviously, they're different from each other, jackass. But when we have 3 groups, it's, okay, so they're different, but we're not really sure which one is like statistically significantly higher or statistically significantly lower or whatever. We don't know that when we just simply reject the null hypothesis for ANOVA. We just know it's different. So we have some characteristics for ANOVA. So on top of having just at least 3 groups to compare, there are some other things to look into as well. So the capital N represents the total number of participants in the study, whereas the lowercase n represents the number of participants in each group. We've kind of discussed this with independent samples t-tests. So again, if we have 3 conditions and we have 10 people in each group, in each condition, then the n, the lowercase n, number of participants per group, well, we have 10, 10, and 10 if there's 10 across the board for each group. And then the total number, that capital N, will just be 30. That's the total number of people altogether. So when it comes to the statistic that we use, ANOVA does not use T because that's for t-tests. ANOVA does not use Z because that's for z-tests. ANOVA decides to use F because, I don't know, why the F? Wouldn't they use a statistic called A to make it easier? I don't know, but it uses the F statistic. So when we calculate step 3 of our null hypothesis testing for ANOVA, we are calculating the F statistic. So another thing that we have is a between and within subjects factor with ANOVA. So ANOVA can be measured through within. So let's say you have a group of people and they're given 3 different conditions each. Just like similar to dependent samples t-tests, it's like, oh, the same group is taking a test before and after. So it's 2 groups that we're comparing, the before and the after group, but it's the same participants. ANOVA can do that as well, except now it's having 3 groups. And then the between subjects factor, the different participants are being tested. So that is if we were to compare our class to Greenwood's class to Burtkin's class, or the no feedback, positive feedback, negative feedback, so long as the people that were in those groups don't switch. You know, one person gets 1 condition and that's all. So ANOVA can be within or between, unlike dependent samples t-test, which can primarily only be within, and independent samples t-test, which would only be between. But I digress. So just to kind of give us some examples of between or within for ANOVA, let's look at this. So we want to determine of these 4 examples, which is a between subjects design for ANOVA and which is within subjects design. Again, between is separate. We have 3 conditions and each condition has 3 completely different groups of people. And within is that all participants, all 30, 50, 20,000, however many people you're testing, the lot of them all have the same, are all being tested on the same 3 conditions. So let's look at that first one. All participants were given 3 snacks and cholesterol was compared. Is this a between or within subjects design? So all participants were given 3 different snacks. So it's not saying, you know, the snacks are being given to separate groups of people. Every single person was given these 3 different types of snacks. So that would be a within subjects design. All participants are encountering all 3 conditions of this variable. So they have the Chex Mix, they have the Reese's, and they have the, I don't know, potato chips. You don't just eat potatoes, at least, I mean, you can. Anyway, so all these participants are given those 3 snacks and their cholesterol was compared throughout. That is a within subjects design. That would be a within subjects ANOVA. Students in 3 different stats classes were tested on their levels of sanity. I've talked about this example several times. This would be a between subjects design. 3 different stats classes. So we have, this is assuming, let's say this is the same semester. So this is kind of the example of our class, Greenwood's class, and Burtkin's class. We're not, you know, there's no flip-flop. You're not going to be in my class for the first week and then Greenwood's the second week and then Burtkin's the third week. This semester has been so much of a mess already. We don't need any more complications with that. So that would be a between subjects design. These 3 different stats classes have 3 different sets of students. So that's a between subjects design. Next, a group of priests, a group of rabbis, and a group of monks went to a bar. Their alcoholic drinks were counted. So we have priests, rabbis, and monks. Those are 3, assumingly, different groups of people. So that would also be a between subjects design for this ANOVA. That would be, you know, the priests aren't going to also be rabbis who aren't also going to be monks. They're 3 separate groups of people. So that would be between subjects. And lastly, a large group of moms were provided 3 techniques of discipline to enact on their children. Obedience was measured. The large group of moms were each provided 3 different techniques of discipline. This is within subjects design. The 3 techniques could be, you know, whatever those techniques are. And each mom in this large group is provided each of those techniques. It's not saying one separate group was provided spanking, another group was provided timeouts, and another group was provided, I don't know, you know, taking stuff away, like no tablets or something. It's just all the moms were given all 3 of these techniques, and we're going to measure the discipline differences between, or obedience differences between them within subjects design, within subjects ANOVA. Okay. So I talked about how ANOVA uses the F statistic, as in why the F are we using this statistic with ANOVA? Oh, gotta get my coffee. So since ANOVA, again, I say ANOVA a lot, but keep in mind that it stands for analysis of variance. It's just, you know, kind of analysis of variance is a little too wordy. But analysis of variance is looking to see how much variation there is, what the variability is between our groups, all 3 of these groups. So it not only refers to the variance between the groups, so how different our class is from Greenwood's class, from Burtkin's class, but it also refers to the variability within those groups. So how much does our class vary within itself? How much does Greenwood's class vary within itself? And how much does Burtkin's class vary within itself? So we're looking at 2 different factors of the variability here. Across the board, how does our class vary from Burtkin's, from Greenwood's? And then how does our class vary within itself? So how do you guys vary from each other? How does Greenwood's class vary from each other? Oh my God. And then how does Burtkin's class vary within itself? Whew, God, that was rough. So just to kind of look at this. So variance, oh, excuse me, I didn't go over the equation. So our F statistic, what we're going to be doing is, there's several steps to get to this point, but ultimately it is a fraction. It is a division of the variance between groups divided by the variance within groups. So the variance contributed to group differences. So how our class is different than Greenwood's is different from Burtkin's. divided by the variance attributed to chance. So just based on the 29 of you in my class right now, the variability between you guys, the 29 of you, that is the variance attributed to chance. That's the variance within groups. And Burtkin's class has their own variance within their group, and Greenwood's class has their own variance between their, or within their group, excuse me. Now I can get to this. So the equation MSBG, so you'll see here, down here, F obtained equals MSBG divided by MSWG, or variance between groups divided by variance within groups. That MS is mean squares, and the BG is between groups divided by mean squares within groups. But essentially, it just means the same as variance. Just, you'll see the MSBG, MSWG a lot. So just know that this is representing variance. But if you really want to get to it, it's mean squares between groups divided by mean squares within groups. So I've illustrated this. So here's just an example, 3 different groups of psychology, sociology, and biology, the type of class, and just numbers, it doesn't matter. Maybe this is their test, their quiz scores, or their sanity levels, or whatever. But for now, let's just kind of look at these. This is just a visual representation of what I've described. So within groups variability is just referring to, you know, these red circles. Only in the psychology, the variability within the psychology group, the variability within the sociology group, and the variability within the biology group. That is within groups variability. That's what that is what we've been dealing with primarily. And then between groups variability is just across the board. How are these different? How is psychology different than sociology, different than biology? Whereas within is just how psychology different from itself, how sociology different from itself, and how's biology different from itself, in a nutshell. So we have degrees of freedom, woohoo, because guess what? We're dealing with samples. We're dealing with, you know, we don't have populations here. We have 3 conditions typically. I tend to, when I talk about ANOVA, I'm going to just stick with 3 groups. It's a little easier that way. But we have 3 groups, but we have 2 different degrees of freedom here. We have the degrees of freedom between groups, and we have the degrees of freedom within groups. Each of these are calculated slightly differently. So for between groups, it's just K minus 1, which if you remember from before, K represents the number of groups we have. So for that previous example, we had psychology, sociology, and biology. Those are 1, 2, 3 groups. So our between groups degrees of freedom would be K, which was 3 minus 1. So it's just 2. So between groups, degrees of freedom is going to be 2 for that example. And then within groups, degrees of freedom is calculated by taking the total number of participants you have across the board. So adding up all the people you have in all 3 of your conditions. So taking that number and subtracting it by the number of groups you have. So just to illustrate this, we're going to go to the next page here. So again, I've stated that degrees of freedom between groups is just taking the number of groups you have, which is represented by K, subtracting 1. So degrees of freedom for between is 2. And then degrees of freedom for within is taking the total number and subtracting by the number of groups you have. So we have 5 in psychology, 1, 2, 3, 4, 5. So N1 equals 5. We have 5 in sociology, and we have 5 in biology. So we have 5 in each group. Since they're all the same, we can just multiply by 3 the number of groups we have to get 15 total people. So that capital N is 15 minus K, the number of groups. So our within groups degrees of freedom is 12. Okay. Now, we have an F table because, of course, we have a table. It wouldn't be statistics if we don't have another friggin' table. But this is different from the T tables, which is certainly different from the Z table. Instead of looking at, oh, the significance within each group, you know, with our T table, we had the significance in the columns, and we would typically go for the 0.05 in a 2-tailed test. With an F distribution table, it is just simply the whole table represents a certain alpha. Now we're going to stick with 0.05 because obviously, but the the rows and the columns is representative of the degrees of freedom. So the numerator and denominator, the numerator, the between groups degrees of freedom, the top number of our fraction here is going to be in the column. So that's going to be this top part here. Degrees of freedom 1 also refers to degrees of freedom BG, between groups. So we go for 2 here because that's our first number, our first degrees of freedom, that 2. So I'm sticking it there. And then the denominator for for degrees of freedom is just the second number, the within groups degrees of freedom. So we had 2 and we have 12 here. So we go over and you'll see that it might be small, but I'm going to post on Canvas an F table so you don't have to keep going back to this and straining your eyeballs. But ultimately, that rounds to 3.89. So our critical value, again, we're using this to find our critical value, our critical F value. So it is 3.89. Now, keep in mind that this is an analysis of variance. Now, before, when we use critical values, I'd always say, oh, it's plus minus 2.60, or, plus minus blah, 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 insert critical value here. However, with an F statistic, we don't have to worry about a negative value. And why do you think that is? Well, my humble listeners, since this is an analysis of variance, we are looking at variability within groups. Now, what is the lowest number that variability can be? Variability can be no less than 0. If your variability is 0, that means everything's the exact same. Everything is the exact same. You can't get any more, same than same. So we don't have any negative values for variability, just as we don't have to worry about a negative critical value when it comes to an analysis of variance. There's no such thing as negative variance. There's no such thing as negative standard deviation or anything like that. It's just positive. So the F values that you have and the F critical values that you'll compare them to will always be positive. Okay. Now that I've drank out of my Golden Girls mug, it's time to look at an example. So here is a one-way between subjects analysis of variance. Okay, so employees at a company were asked to rate their stress level in the workplace. 30 total employees responded, where 10 stated their perceived stress was low, 10 stated it was moderate, and 10 stated that their perceived stress was high. These groups were then asked how long they think they'd continue working for the company in years. So they have answered this questionnaire regarding their stress, and the researchers have kind of separated them into 3 different groups. Overall, 10 people said their stress was low, 10 said it was moderate, and 10 said it was really high. So those are our 3 groups we're working with, the perceived stress being low, moderate, and high. Okay. And then these numbers here represent how long they'd anticipate working for this company in years. So when you have, to find N, I know I've kind of mentioned this earlier with the previous example, but to find the total number of people in your group, so long as the sample sizes are all equal, so we have 10 in each group here, 10, 10, and 10, you can just take the number of participants times the number of groups. 10 times 3, we have 30 total participants. So, not to insult intelligence, but if you're trying to find your capital N, that total number of people, so long as your sample sizes are all the same size, you can just simply multiply by the number of groups you have. Okay, so now let's get into hypothesis testing. So our null hypothesis is saying that the group means do not vary between groups. So again, this is an analysis of variance. So that's why we have the null hypothesis is stating that the variance between our groups is equal to 0. Because again, null hypothesis is saying these groups are the same. They're all similar. There's no difference between them, etc. So the null hypothesis states that there's, nothing special. There's no one higher or lower or any direction. They're all pretty much the same. So that's why with an analysis of variance, when your variance or any sort of variability is equal to 0, everything's the same. Hence why we have a 0 for variability in our null hypothesis. Now, our alternative hypothesis is saying that the group means the group variability will be greater than 0. We don't have to worry about, oh, not equal to 0, because again, variability can only be positive or 0. It cannot be negative whatsoever. So for an analysis of variance alternative hypothesis, it's always going to be greater than 0. There's no other option. It's impossible to have another option. So simply, this is how you would state the hypotheses. These will be the same for any between subjects one-way ANOVA. It's always going to be the null hypothesis is variance of the means is equal to 0, and the alternative hypothesis is always going to be the variance of the means is greater than 0. Okay. So step 2. We have our alternative and null hypotheses at this point. The variance of the groups is equal to 0 for null. The variance of the groups is greater than 0 for alternative. So now let's get into step 2, setting the criteria. Oh yeah. So we're just gonna stick with alpha set at 0.05 because that's the best, or well, not the best, but it's a good threshold to have. So before we set the criteria, we have to find our degrees of freedom. Just like how we had to do for t-tests, we had to start with degrees of freedom. Same thing here. So we have degrees of freedom for between groups is equal to number of groups minus 1. So we have the low, moderate, and high. So our k is equal to 3 minus 1. Our between groups degrees of freedom is equal to 2. And then our within groups degrees of freedom is taking the total number of people and subtracting it by the number of groups we have. So we had 10 in each group. 10 times 3 is 30. We have 30 total people. And then we we subtract the number of groups, which was 3. Our within groups degrees of freedom is 27. So we can represent this as 2 over 27. So then when we go to our F table, we know which one is which. So again, this first number, degrees of freedom 1, is representative of that between groups. So we have 2, and then 27 is way down here. So we have the number that lines up there is 3.35. I'm rounding it to 2 decimal places just to make it a little easier. But our critical F value is 3.35. So we have our null and alternative hypotheses, and we have our critical F value, what the F value that we will compare our F statistic to determine if we will retain or reject the null hypothesis. We are good to go. Now let's go on to step 3 to calculate the test statistic. Now, with ANOVA, with an analysis of variance, step 3 is a doozy. There are several things that we need to do to calculate the F statistic. First, we need to calculate the preliminary calculations. After that, the intermediate. Then we calculate the sum of squares, and then we can complete the F table. So, let's start with the preliminary calculations. So, I'm gonna get my handy dandy whiteboard for this. So what we have to do for the preliminary is we have to find the sum of scores in each group. So this is going to be adding up the scores for just one group at a time, just within one group. So we're gonna have 1 for each group. So for our low perceived stress, we're gonna add all those up. For our moderate perceived stress, we're gonna add all those up. And for our high perceived stress, we're gonna add all those up. Okay, so that's the first one. For the next one, the sum of all the scores in the group combined, that's just, well, that's adding them all together. That is just taking, we're just adding up every single possible score for every single person all together. So that first one, it's just within one group. And the second one, the grand total is adding up every single individual score in all 30 people instead of just 10, 10, and 10. So the next one, the sum of the squared scores in each group, we're gonna have 1 for each group. We're gonna square all the scores in the low group, square all the scores for the moderate group, square all the scores for the high group. And we're going to add up the scores that were squared within each group. So the low group is going to have all their scores, their squared scores added. The moderate group is going to have the sum of all their squared scores, and the high group is going to have the sum of all of their squared scores. So one for each group. And it's going to be the squared scores. The next one, you've guessed it, just like how the grand total for the first example we have, is just adding up all the sum of the scores combined. Now we're adding up for this sum sigma x squared t. That's just adding up all the squared scores in all the groups. All squared scores sum. Okay. And then we have our lowercase n, the number of participants in each group. So again, lowercase n is just number of participants in group. And then our k is the number of groups we have. Ooh. My pen is running out of ink. That is profoundly irritating. Okay. Okay, so just keep in mind that what we have to do is add up the scores in each group. We have to find a total for each individual group and then add those together. We have to square the scores in each group, add those up for within each group, and then add all those scores together. So for that first one, the sum of scores in each group, we're just taking these raw numbers, the 3.4, 3.2, 3, 3, 3.5, etc. And we have the sum of the scores for the low group, 34.30, which is just, again, adding all of these. To get the squared scores, we square all the groups. We square the scores in each group, and that gives us, and add them together, which gives us this, 109.90, or for this one, 119.07, 90.5. And we, square each of these scores. So 3.5 squared plus 3.6 squared plus 2.7 squared, gives us this number. And we've done that for each of these groups. And then once we've done all that, we add them all together. So I've done this for each of the groups here. So, excuse me. So each of the groups, 3.4 plus 3.2, that gives us this EX1, or excuse me, sigma X, the sum of the scores for group 1, the sum of the scores for group 2. Once we add all these together, we get 33. And the sum of the scores for group 3 is just 2.9 plus 3 plus 2.6, etc., 29.8. You can just add all these numbers together, 34.3 plus 33 plus 29.8 to get 97.10 or 0.1. And that gives us the sum of all the total scores. So the sum of the just scores for everybody, so all 30 of these people. Next, we square 3.4 squared plus 3.2 squared plus 3 squared plus 3 squared down the board. And that gives us this number here. The sum of the squared scores for group 1 is 119.07. And then we do the same thing here, 3.5 squared plus 3.6 squared plus 2.7 squared, blah, 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 blah. That gives us the squared score sum of group 2 to be 109.9. And then we do the same thing for the last group, for the high perceived stress group. We have 2.9 squared plus 3 squared plus 2.6 squared, and we add all those together, and that gives us 90.5 squared, or not squared, excuse me, 90.50 for the sum of the squared scores for group 3. Whew. And then we add all of those together, and that gives us 319.47. Okay, so my pen is running out of ink, and I don't know how well you can see this, but we have 3 different groups here. So I'm just going to write these down, and I'll show you guys as I'm doing it. So we have, first what I'm writing down is this here, the sum of the group 1, of just the raw scores, not squaring them, just the sum of the scores in group 1 is 34.30. Oh God, my pen is running out of ink and it's pissing me off. All right, I gotta erase all this crap because I have too much of it. Okay. In fact, I think I'm going to get a different pen because this is garbage. Luckily, I have pens. Okay. So, I'm gonna rewrite this. Okay. So to move forward, remember, these are our beginning, these are our preliminary calculations. Oh, excuse me, I just skipped a step here. Sorry about that. So we have damn it, I keep doing that. So the sum of the scores in group 1 is 34.30. The sum of scores in group 2 is equal to 33.00. Might as well stick with it. And the sum of scores in group 3 is equal to 29.80. Okay. Now the sum of the squared scores for group 1 is equal to 119.07. The sum of the squared scores in group 2 is equal to 109.90. And the sum of scores for the sum of the squared scores for group 3 is equal to 90.50. Now we have the sum of the total scores to be 97.10. So adding up the 34.4, or excuse me, the 34.3 plus 33 plus 29.8 gives us 97.10. And the sum of all the squared scores is equal to 319.47. Again, just adding up that 119.07, 109.90, etc. So I've written out, it's kind of sloppy, but at least you can friggin' see it. So we have the sum of scores for everything here. So that completes our preliminary calculations. Whew. Okay. Now, intermediate calculations. Now notice that in my thing here, on my whiteboard, I've written the notations. I suggest that if you're going to do this by hand, you do the same because it makes this part a lot easier. Now keep in mind here, I don't know how well you can see it. But those represent the sums of all of them. Okay, so first of the intermediate calculations, the correction factor. So this is, again, here's the notation, the sigma xt squared. So, well, sigma xt in parentheses, and then that number is squared, divided by the total sample size. So the sum of scores in all groups combined, which was 97.10. 97.10. Put that number in parentheses and square that, divide by 30. So that gives us the correction factor equal to 314.28. Okay. Next, we divide the sum of squared scores in each group by the sample size in each group. So look at this, I'm on number 2 now. So we have the sum of the squared scores, or excuse me, the sum of each of the scores squared for each group divided by their sample size. Okay, so that means we're taking just, when we added up all the numbers, not squaring them, just adding them all up, and found the sum of that, we square that number. It gets weird, it gets a little complicated, but That's why I suggest you kind of keep in mind the notations and just plug in the numbers in the parentheses and then keep the squared there, because the squared is separate for this particular example. Okay, so it's 34.3 squared divided by 10 plus 33 squared divided by 10 plus 29.8 squared divided by 10. And that gives us, hang on a second. Oops, I forgot this does not have an eraser on the back of it. Right. Okay. Okay. So to do the intermediate calculations, we have to do those preliminary calculations first. So again, it's this sum of the scores in all groups combined, and we're squaring that number, divide by 30 to get that correction factor at the top. So that gives us 314.28. Once we take the sum of the scores for each group, we square that number and divide by the sample size for the second calculation here. And we add each of those together, each of those fractions together. And that gives us 315.35. Next, we just restate the sum of the squared scores in all groups combined. So again, this number 3 here is just, we square every score and we add all 30 of those squared scores together. And that gives us 319.47. Okay, so we've done step 2. Now let's go to step 3. So this is to compute the sum of squares. So there's 3 different sum of squares that we need to calculate. First, we have the sum of squares between groups. So we've already calculated these numbers we need. We have the sum of squares for the, or between groups equals, once we took each of the individual sums of the groups, squared those and divide by the sample size. Remember, that was the one that had our 3 different fractions, each were divided by 10 in the previous slide. That gave us that first number, that 315.35. And we subtract it by the correction factor, that the total sum of all of the scores, square that number, divide by the total number of people. That gave us 314.28. So once we, to calculate that sum of squares for between groups, it's just taking one of those numbers and subtracting it from the other. So 315.35 minus 314.28 is equal to 1.07. Oops, I messed up. Whew. Now we take to get the sum of squares total, it is taking the squared sum of all the numbers. So we've squared each of the observations, each of the data points, and added all those numbers together. So that's that first number in sum of squares total here, which we actually calculated back in step 1. So 319.47 minus the correction factor. Again, that's the same number we used here, which is the same number we calculated here. So we have 319.47 minus 314.28. That gives us a sum of squares total of 5.19. Huh. And then the sum of squares within groups, that's the last one you'll need to do, because now you just take the sum of squares total minus the sum of squares between groups. So you take this 519, which you calculated here for sum of squares total, boom, 519, bam, minus the sum of squares between groups, boom, we calculated that here, minus 1.07 equals 4.12. So our sum of squares within groups is equal to 4.12. Okay. Now, we complete the F table. Now we get crack-a-lackin'. So we have our sum of squares. I've put in the numbers here, and we have our between groups, our within groups, and our total. So that is this F table here. These numbers, we just calculated. So if it makes it easier for you to fill this out, as you see it here, you can. So we have our source of variation for between, within, and the total. So our sum of squares, again, we've just calculated that. Our sum of squares for between was 1.07. Our sum of squares for within was 4.12. And our total was 5.19. Degrees of freedom between groups, we calculate by taking the number of groups minus 1. That gives us 2. Within groups, it's the total number of people, 30, minus K, number of groups, that's equal to 27. And we don't really worry about the degrees of freedom for the total here. We're just more so concerned we're between and within. Whew. Now remember when we talked about MS like 20 freaking years ago, how that is the mean squared, or the mean squared for between groups, and then the mean squared for within groups, which essentially was variance. Keep in mind, if you remember our F statistic, how to get that from 70 billion years ago, it seems, it's taking the variance between groups divided by the variance within groups. AKA, to get this number, to get our F statistic, we take the number from here and divide it by the number from this square. Okay. But first, we got to find the numbers in those squares first. Ain't that right? Yes. My daughter is knocking on the door. But I don't think she's going to answer. Okay. So we have our between group sum of squares. So to calculate the, hello, darling. Hi. Honey, I'm recording right now. I'm recording, honey. You need to go here. All right. Okay, Amelia.
Huh?
Hi.
Hi.
Okay. So, can you say analysis of variance?
Thank you.
No, you can't see my pen.
I want to red squawk.
Mm-hmm. Hey.
Need to million of that.
Yeah? I love you.
I need red.
You need red?
Yeah.
Honey, not right now, okay?
I need to make a million, make me all colors.
I know you want to make all the colors, honey.
Will you come in, Yaya?
No, we're talking about analysis of variance right now, sweetie pie.
Okay.
Oh, you excited?
Look at check the button and then I'll look at Earth my dad.
Oh, no, we're not going to talk to Dad right now, honey.
Look at Earth on the dad.
Hey, can you go to the living room and tickle Sissy?
Yeah.
Okay.
I like to wake up in the morning.
You woke up in the morning. Yes, you did.
I do.
Yeah.
I okay. Say, I love you.
I love you.
What did you say?
Honey, you gotta go to the living room, okay? Yes, you've woken up, honey. Go get your butt done. It's fine. Amelia, I love you. I'll see you later, okay, sweetie pie? It's all right. I love you guys. So, as a brief break, just so you know, I know that with the shelter in place being in place, I know how difficult it is for everyone, not just students, but just, well, everyone, not just in school or not. I know how difficult it can be to be, you know, you guys were anticipating this class to be in person. It turned out to be online. That sucks. I hate it too. I wasn't looking forward to teaching in person, and now it's online. So when it comes to, you know, I know a lot of you guys might have kids or younger siblings possibly that you're taking care of. I understand how, you know, this class can kind of fall by the wayside because, hey, people can be a lot more important than, you know, an analysis of variance or frickin' completing an F table, for God's sakes. But just let me know if you have any of these issues, you know, if you're taking care of siblings or kids or even older family members, just let me know. You know, I can help you guys try to, you know, get things situated or at least kind of be more lenient in terms of getting things taken care of for you. Because I know it's difficult, you know, everyone being at home, everyone having a shelter in place, it kind of, you know, it's difficult to keep in mind that we still have class. So just, that was a perfect segue. Thank you, Amelia. God, I love her. Anyway, so for back to the F table. So again, remember that for the obtained F statistic, we have to take the variance between groups and divide it by the variance within groups. That's what that MS is essentially saying, that variance or mean squares. So to calculate that, we have to take the sum of squares for between groups and divide it by the degrees of freedom for between groups. And then we have to do for within groups, sum of squares within groups divided by degrees of freedom within groups. We have all these numbers here. We're freaking ready to go. All right. So we take the sum of squares between groups, this 1.07, and divide by the degrees of freedom between groups, which is 2, to give us the variance between groups. And then for this, the sum of squares within groups, which is right here, and divide it by the degrees of freedom within groups, which is right there. And that gives us our variance for within groups. Whew. Okay, so like I said, we have our equations. So I've already kind of discussed this. But for that first group, that variance for between groups, it's taking the sum of squares between groups, that 1.07 divided by the degrees of freedom. That gives us the variance for between groups equal to 0.535. Then the variance for within groups is taken by, is calculated by the sum of squares within groups divided by degrees of freedom within groups. So 4.12 divided by 27, that gives us the variance for within groups equal to 0.152. Finally, after 17 years of calculations and F statistics and between groups and within groups and sum and squares and finally we can calculate our F statistic, which is taken by taking the variance for between groups and divided by the variance for within groups. And that gives us 0.535 divided by 0.152. That gives us 3.52 for our F statistic. So F is equal to 3.52. And holy moly, now we can complete the F table. So again, this MS here was calculated, the MSBG is calculated by 1.07 divided by 2, or divided by the degrees of freedom here. And then this was calculated by 4.12 divided by 27. And to get this F obtained value, this F statistic, we just did, it's literally set up for us the way this table is set up, because we take 0.535 and divide it by 0.152. That gives us 3.52. Oh my God. So now we make a decision. Now we compare our F statistic to the critical F value. If you remember back from, again, 20 bazillion friggin' years ago, our critical F value was 3.35 when we looked at that F table using the degrees of freedom between over degrees of freedom within, and we found, hey, we have, you know, our critical F value is 3.35. Since our F statistic is greater than the F value, we will reject the null hypothesis. This is telling us that the group means do vary across the 3 different employee stress groups. So the low is different from the moderate, is different from the high. We don't know, however, which one had higher or lower levels of how long they would stay at the company in years. To do that, we have to do a post hoc test. So I'm just going to go over that quickly. We're not going to calculate post hoc tests. And I'll also discuss what I will expect you guys to be able to know. Because FYI, you're not going to be calculating these by hand because it's garbage. You're going to be reading a table and interpreting it from there. Okay. So first, if we, what I want you guys to know first off is, when do you conduct a post hoc test? Now, keep in mind what I said at the beginning of the lecture, when I said, okay, when we reject the null hypothesis for an ANOVA, for an analysis of variance, that's just telling us that the groups are different. Now, since we have more than 2 groups, we have at least 3, rejecting the null hypothesis is not telling us, oh, well, the people that had high stress are going to perceive themselves to be working here for less than the low stress, or, oh, the moderate stress had the highest, or, oh, the low stress had the lowest, or whatever. ANOVA's rejection of the null hypothesis tells us nothing of that. What we need to do is a post hoc test. We only conduct a post hoc test when we reject the null hypothesis. If we retain the null hypothesis for ANOVA, we don't have to do shit. We just stop there and say, all right, we retain it. We cool, let's stop. But when we reject it, again, that's saying the groups are different, but we don't know how they're different. Post hoc tests are going to tell us which groups are different. Which ones are the groups significantly higher or lower or whatever. One of the most commonly used post hoc tests for between subjects ANOVA is Tukey's test, is just a Tukey's post hoc test. So in a nutshell, it's essentially just comparing all the groups to each other. This is kind of done to determine which one is significantly different. These can be calculated by hand, although many times people will use statistical programs to do this. So like something like SPSS will do this for you. I don't want you guys to calculate post hoc tests. That is not my concern. What I want you guys to know about post hoc tests in terms of ANOVA is just when you will conduct them. When do you have to do it? Only when you reject the null hypothesis for ANOVA. What about when you retain the null hypothesis for ANOVA? Then don't worry about a post hoc test. It only comes up when you reject. Okay, that's literally it. Okay, so in terms of the exam, this is what I'm going to show you. This is something that is similar to what your exam would be, a question on the exam relating to ANOVA. So what I would want you guys to do is calculate the F statistic, let's say, determine if you have statistical significance and if you're going to conduct a post hoc test. So using this, let's do it. So to start, I'm just going to go over how to read this summary, this ANOVA readout for a second. So you have your 3 groups, Tammy, you and your supervisor, and you have a count. So how many is in each group? So let's say this is just the, I don't know, the number of reviews you have or something, I don't know. And each, so Tammy, there were 18 for Tammy, 19 for you, and 20 for your supervisor, and your average is here, your variance is here. But this is just the 3 groups you have. So this summary up here shows your groups. Down here is where the analysis really gets cracking. So remember that to calculate the F statistic, we had to do MSBG divided by MSWG. So 10 divided by 2, our F statistic is 5. Again, looking at a readout, it's super easy if you don't have the F statistic to just plug it in. And these numbers are pretty simplistic, but you know how I provide my tests. You know that I don't require calculators. So you know that my math on them is going to be fairly simple. What needs to be done on your part is just knowing, hey, what do I do? Do I divide, you know, what do I have to do to calculate the F statistic? Looking at it, it's literally right in front of you. 10 over 2, and that gives you F. So 10 divided by 2, our F statistic is equal to 5. Okay. Now, we have an F statistic of 5. So then our critical F value is 3.17. Okay. So remember, with F statistics, to calculate statistical significance, We don't have to worry about the whole less than thing. We don't have to worry about negative Fs. We only think about positive Fs. So is our F statistic of 5 greater than the F critical value of 3.17? Yes, it is. So that would mean we reject the null hypothesis. We have statistical significance. And finally, another question I would ask on an exam would be, would you conduct a post hoc test? Yes or no? Well, when do we conduct post hoc tests? When we reject the null hypothesis. Did we reject the null hypothesis? Yes, we did, because our F statistic was equal to 5, which is greater than 3.17, this F critical value here. And how did we get that 5 for our F statistic? We took our mean squares, our variance we took our mean squares between groups, that 10, and divided by the mean squares within groups 2 to get us 5. So those would be the 3 questions I would ask on an exam in relation to ANOVA when I provide a handout, or a readout like this. What is F? What is your F statistic? Oh, 5. Do we have statistical significance? Would you retain or reject the null hypothesis with this information? Well, our 5 is greater than this 3.17, so we reject. And finally, would you conduct a post hoc test, yes or no? Well, yes, we would conduct a post hoc test because we rejected the null hypothesis. And that's that. Okay, so that was analysis of variance. It's a little complicated. It's really long and drawn out in terms of calculating all of the individual numbers. But like I said, for the exam, I'm more so going to test you guys on the readout and just knowing, at least at the very at the very least, knowing that it's MSBG divided by MSWG. And that information will be provided on any readouts that I give you. I won't have the p-value on there because I don't want you guys to see the p-value and be able to kind of cheat your way to it. Ultimately, I'm just seeing, can you calculate the F statistic? Can you compare the F statistic to the F critical value to determine significance? And with that decision being made of statistical significance, are you going to use a post hoc test, yes or no? If you have any questions in relations to ANOVA, be sure to email me or contact me, however you, well, email or message me through Canvas. This is going to be the last thing we cover before the exam. So I'm going to send an announcement about the exam review. I'm thinking we'll do another Zoom, we'll do a Zoom conference call with as many people as we can, because I still want you guys to ask me questions for things you don't understand. And I'm anticipating that that could be a bit of a longer session. If it runs a little long, that's fine with me considering the situation that we're in. But ultimately, I still want to provide you guys the opportunity to ask questions of me and be able to get after it and me to answer those questions for you. And also, I missed your faces. So like, it'd be nice to see, my students again. It'd be nice to see you guys again. Anyway, so that is ANOVA. That's the analysis of variance, the last thing that's going to be on our exam. So I suggest that, you go over this. Next thing that we do in the class is going to be the exam. So if you have questions, let me know and I will answer them for you. Goodbye.